Hey everybody, it's Mr. Allred here, and I'm going to talk about optimization, which basically means to optimize what you have. So you can look at this in two ways. One, the example that we have here, you're given so much material and you want to make the most you can out of it, use it the most effectively. Another example we'll do later, maybe you want to make so many things and you want to use the least amount of material possible. So one, you want to make the most. The other, you want to use the least to get what you want. Usually that's the two main types of problems we'll see. There's other variations, but they all depend upon you maximizing some characteristic. So let's start with an example, and this is an example you can do in pre-calculus. You don't really need calculus to solve this problem, but we will solve it using derivatives. But let's start off with you have 300 feet of fence, and you wish to make a rectangular enclosure that has 3 sections. And I've drawn a little picture here, so possibly some way to picture this in problems you've seen before. Maybe you're trying to make a pig pen and you got 3 pigs, they don't get along, so you need to make it in 3 sections. Or maybe you're trying to divide up your garden into 3 sections, but you have to put a fence around it to keep some animals out. Let's see here. So what is the max area you can enclose? Well, let me do a little bit of a description here, or a little bit of trial and error. So let's do something kind of silly here. Let's start off with the fence and let's make it 2 feet wide. So if we use all 300 feet of fence, it'll be 2 feet wide and it'll be really long. Okay, so those are supposed to be straight, but this is 2, 2, 2, 2. So basically I've used 8 feet on the 4 sections that go across, so that leaves me 292 left. And if I divide that by 2 for the sides, I get 146. So this side over here will be 146 feet, and this side, well, excuse me, the other side would be 146 feet. So you could add, ooh, that's more than 300, isn't it? No, that is 300. You could add all those numbers I have there together, 146, 146, 2, 2, 2, 2, and that will come up to 300 feet of fence. So we've used all that we have. But just to see what that does for us, the area would be 2 feet by 146 feet. And if we multiply that, I shouldn't have to pick up a calculator, but let's see. 2 times 146. A number we've seen very recently, 292 feet squared. So we can see this may not be very realistic because if we did make it 2 feet wide, maybe that wouldn't be very effective as far as my pigs having much fun in there. But it does show how much land or area we would enclose. So let's kind of change our numbers up a little bit and do it again. So let's say we make it 5 feet wide. Okay, so it's going to be wider, so it won't be as long, and don't think I'm drawing to scale. But 5, 5, 5. And then there we've used 20 feet of fence, so that leaves us 280. And if we take 280, divide it by 2, we get 140. So it almost looks very similar. Okay, it's still very long. It's a little bit wider, so it probably doesn't look like it's all that different. But if we come down here and we see what our 5 by 140 feet of fence does, we'll multiply those together. 5 times 140, I get 700 feet squared, or 700 square feet of area. So I've enclosed much more land and using the same amount of fence. So I've used my fence more effectively here. My hogs or my pigs have more room to run around, or I have a bigger garden if we're looking at it that way. So I've used it much more effectively, much more efficiently. But have I used it the most efficient way possible? So let's see. Let's kind of continue on. So now let's actually try to solve the problem. So let's draw a generic one, and if my lines aren't straight, I apologize. Okay, so let's slide this up. Oops, sorry. Okay, now I can get rid of those. So in this drawing, we have the same thing that we had before, and we have, instead of starting off with the measurement there, let's just give it a name. We'll call that width X. We could call it something else, or we could start with the length. It's not really important. But what you should remember is that we had 300 feet of fence to start with. So right there, we have used 4x. Okay, so we used 4x on width. So that gives us 300 minus 4x left. Now that would be for the both lengths here. Okay. So if I took that 300 minus 4x and divide it by 2, I would get 150 minus 2x, which would be 1 length. Okay. There's other ways we could do this, but another way to talk about how much that is left for both sides is to write it in a single variable. Because we could call the width x and then the length y, but then we've got two different things, and we've got to come back later and talk about how they're related. So if you add all these together, 150 plus 150 is 300. You've got minus 2x plus 4x's. It gives you that 300. So basically what we've done here is we've written the length and the width both in x. And that's very important, because what we're thinking here is I'm trying to maximize area. So it said find the max area. So the reason I've done all this is we're going to work with the area formula, which you usually think of as length times width, but now we can call it 150 minus 2x times x if we want to call it length times width. Now because we're finding the max area, that means derivative. Set equal, do you remember? To 0. So remember when we were trying to find maximum and minimums? We would take a derivative, we would set it equal to 0. We might do a little bit extra work after that, but this whole process here has been getting to a formula that we can take the derivative of and set it equal to 0. Okay? So let's clean this up before we take a derivative. So area would be 150x minus 2x squared. Okay. So derivative we'll call it A prime, would be 150. We're just using power rules here. 150 minus 4x. Then we can set it equal to 0. Remember, saying the derivative equal to 0 means that we're saying the slope is 0, which means it goes flat if we're thinking about it graphically, which could be a max or a min depending on the context. Okay. So if I solve this, I bring the 4x over, I have 4x equals 150, I get x equals, calculator time, 150 divided by 4, 37.5 feet. That is for the x. So that x that we've got there is for the width. And if we plug that in for the x with the length, that length would be 75 feet. You can calculate that. But we can come back and say that area is the length times the width. So 37.5 feet times 75 feet. And let's see. 37.5 times 75 gives me, wow, 2,812 and a half square feet of area. And that is the max area. So I'm sure you could just play with it and guess and check different lengths and widths to see when you are getting close to the max. You'll see it go up, you'll see it go down. But especially here with the 37.5 feet, you might just miss that if you're trying to stay with whole numbers. You might try 37, you might try 38, and you might get the same thing. So you might just assume it's the same in both those places, and you might not really think about the fact that it's gone up a little bit and then back down to get to the next one. But this is what we've got. We're going to be given some type of, let me come in here. We're going to be given some type of parameter or restraint, kind of like we were given 300 feet of fence here. And we're going to be asked to find the maximum or minimum of something else. So think about what we were given here. We were given, just to kind of sum up, we were given a set perimeter. And we're asked to max the area. So one was set, and we were trying to use that set figure, that set amount of fence, to make the biggest thing possible. All right, good job.